We go into session 2, which is on science and governance for MAR. And the next speaker is Professor Simon Stisen from GEOS, Geological Survey of Denmark and Greenland. So there you go, Simon.
Thank you very much. Hi, everybody. I hope people are back. I'll just start by sharing my screen. Do you see my screen?
Yes, it looks good.
Okay, good. Thank you very much. So my name is Simon Stisen, and I'm from the Geological Survey of Denmark and Greenland, and I'm coordinating this MAR China project. I would like to talk today about groundwater resources modeling in the North China Plain, which is a part of this project. And I would also like to just start by acknowledging that this work that I'll be presenting is really carried out by Grit and Julian and Wensi, and I'm presenting some of their results and progress, and it's also in a collaboration with Xinghe and Yan Shen. The outline is a little bit about our MAR China project, then just one slide on the North China Plain and some of the challenges that has been presented previously today. I'll tell you a little bit about the modeling framework that we're working on and our calibration strategy, and then we're outlining some managed aquifer recharge scenarios in the end. So the MAR China project is funded by the Danish Development Agency, DANIDA, and it's a collaboration between these institutions: SOSTEC, University of Jinan, BWSGI, IWHR, GEOS, and Nordic. The project is broadly focusing on managed aquifer recharge in the North China Plains, specifically at both quantitative aspects and qualitative aspects, and also increased knowledge among stakeholders. So we have 3 work packages, and you will see results from those today. You've already seen some results from Wei-Ping Wen, and Jan has also presented some of the things that are a part of the dissemination of and knowledge sharing. I'll talk about work package 1, and later Yunji will tell something about the water quality issues, and Binghua will also talk about the guidelines, which belongs to the VP3. So the North China Plain, as you've heard previously, most of you know better than me, it has some challenges due to intensive agriculture, high population density, and this has resulted in this interbasin transfers, mainly from the south to north water transfer, trying to close some of the water gaps. And there's still a clear groundwater deficit in this region, and this is why we're looking at the water resources and MAR as a potential. So the modeling that we're doing here in work package 1 is largely focusing on developing a large-scale model that can analyze scenarios of MAR and what are the potentials of MAR in relation to other water-saving technologies. So we're building on existing groundwater models, and we've identified some potentials for model improvements, and these are mainly on the boundary conditions, what goes in and out of the model area, specifically also spatially distributed quantification of irrigation in time and space, also distributing in detail the water demands, and then looking into several objectives in the model calibration and uncertainty framework. So basically what we would like to do, the area on the left, the larger area, is the Haihe River Basin with the mountain regions that are in white here. And then we have the focus area, which is where we define the North China Plain. And this is where we look doing the groundwater modeling. So we would basically like to improve the fluxes in and out of this both from irrigation losses and surface water and groundwater flows into the model area. So if we look at the first part here, we are doing models both on the whole North China Plain and also the Baoding area. And we are improving the model boundaries by looking at an even larger scale model of the whole Haihe model, set up in a different model, so more of a surface water balance model. So we're using that information to assess the flow boundaries at the boundary of our model. And we're also incorporating the south to north water transfer flows into the model. Then Julian has spent a lot of time on quantifying irrigation in the North China Plain. And the reason behind the approach that he has, the reasoning behind the approach he's used is to look at the satellite data describing this very distinct pattern in time and space originating from the irrigation. So on the left here, you have the NDVI, which is a vegetation index that you can monitor from satellites in April. That's the peak of the winter wheat. And then later in June, the winter wheat is harvested. So the North China Plain area has now much lower vegetation. And then in August, there's a second peak that is the summer maize, which is mainly sustained by natural rainfall. But the winter wheat is in a dry period, so that is sustained largely by irrigation. So the approach that Julian has used is to do like dual modeling of the evapotranspiration. He models it both with a hydrological model that does not include the irrigation component, so it simulates natural evapotranspiration as it would occur with natural climate and vegetation. And then he uses satellite data to estimate the real evapotranspiration, which of course includes irrigation. And then he subtracts the two to get a signal of what is actually the loss of water for irrigation. So it's not the pumping per se, but it is the water that is lost due to pumping for irrigation. And this has both a spatial pattern, as you saw, and it also has a seasonal pattern. So it's very clear that it is this winter wheat production that really has this separation between a natural system, how the evaporation would look, and this system where the human intervene and increase the irrigation, the evaporation loss by irrigation. So basically the difference between these two curves. And this was published last year in Water Resources Research and produces these nice maps of annual irrigation loss that we can use in our models. And it also estimates the annual loss due to irrigation. And Julian also looked into this, seems to be for this period, 2002 to 2016, relatively steady amount of irrigation, but there's an increase in the production, which means that there's an increase in water use efficiency over this period. This is also what Sin talked about in his first presentation. So this information is really critical to have this time and space data for our models. Next, Grit has looked into the distribution of water demands, and here she's used the reported water consumptions or demands for different districts and provinces. And she's then distributed it according to different criteria, mainly based on population density. So this means that we now can split the water demand into urban, industrial, and ecological water requirements, and then the irrigation part. So we have these 4 maps, and these all vary in time and space at a very high resolution. So we can add this to the model. Then the geological model is quite coarse. We have quite limited information on the subsurface. We base it on the existing interpretations from the China Geological Survey. And then we have observation wells of groundwater heads to monitor the level and the trends in the groundwater. This is for the whole North China Plain. And then Wincy, she's worked a lot on the Baoding area that you see here in the blue area. This is also a large area, but it has a higher density of information on both the stratigraphy, but also groundwater level observations. So Wincy has used all these borehole data to go into more detail on the geological structure of this area and building a geostatistical model for the subsurface that can then be used for the model simulation of groundwater flow. And when we calibrate these models, we have what we call objective functions. That's basically the target, what we want the model to be able to represent. And here we are working in this project with what we call a multi-objective calibration approach, where we have actually a lot of different targets. So we both want the model to, for instance, be able to simulate the general groundwater level, but also the trend over time. In most cases here, decreasing trend in groundwater levels, and the seasonal variation between the rainy season and the dry season. Then we have other objectives like the evapotranspiration and the pattern of that we estimate from satellite, and also the surface water system and what discharges to the sea to keep track of the overall water balance. So in this approach, with a lot of different targets, we use a calibration approach where we do not want to estimate one specific parameter set, but we run the model hundreds of times. And then we see that there's always a trade-off between the model being very good at predicting one particular variable or another. So there's this trade-off between, and that means that there's not a single solution in the model. There's multiple possible plausible parameter sets and model solutions. And in our case with 5, it's actually more complex than the 2-dimensional case. It's actually 5 dimensions to this space. So we carry this uncertainty into the scenarios by selecting several parameter sets, so we have several plausible models. And that is a way of trying to deal with the uncertainty of these kind of model predictions. So in the end, what we're doing is we are running different scenarios to try to shed some light of the potential of managed aquifer recharge in the North China Plain on a large scale. We have a baseline period from 2000 to 2013. And there's one scenario on Ma. For now, it is based on infiltration of excess peak flow from the major rivers flowing into the North China Plain from the Haihei Mountains. And then we're comparing that to scenarios of utilizing the south to north water to substitute groundwater pumping and also consider return flow. The third alternative is to look at reducing the irrigation amount for winter wheat production. So the idea is to compare these different scenarios. What kind of magnitude would that, what would be the response of these kind of changes, and how would that vary in time and space? So for the scenario on peak flow, the idea like stormwater flow is to say that we have time series, simulated time series of the river flow from these rivers flowing into our area. And if we assume that the peak flow above the 85th percentile is water that would normally not be utilized, it would flow through this region, we imagine that it would be possible to hold back a fraction of that peak flow, 5, 10, or 15% on an annual basis, by infiltrating it along the rivers in this Piedmont area where there's a good infiltration capacity. So we are designing these kind of scenarios, and it's a flexible system. Of course, we could design a lot of other scenarios and different scenarios, and we're also very interested in getting some feedback on how to design these scenarios. So the key messages today is that we've worked on improving this water budget of a groundwater flow model. So a three-dimensional groundwater flow model that simulates the whole North China Plain, and also a more detailed model for the Baoding Plain. We've worked a lot on improving the quantification of irrigation. And also we're trying to place this scenario modeling in an uncertainty framework. So we've now built a model that's capable of analyzing a range of large-scale Mars scenarios and other management scenarios. And this scenario modeling is work in progress. So with that, I would like to thank you for your attention, and you're welcome to have a look at our webpage for more details on the Managed Aquifer project. Thank you.
Thank you, Simon, for your presentation. There are no questions or raising hands at the moment, so I think we will go on to the next presentation of Assistant Professor Yunji Ma from SOSTECH. Have we lost her? Is Jan? Do we have Jan and okay, yeah.
Okay, so Simon, can you stop the share of the screen? Simon?
We can see it now.
We can see
okay, sorry.
we can see your presentation now.
Okay. Okay, so good day, everyone. Also is pleased to give this talk in the Managed China workshop, which is about reclaimed water for managed aquifer recharge. So managing the conventional and emerging water quality risks. Okay, sorry, just a second. Okay, so here we go now. Actually, 1 hour ago, I think Professor Wu from Tsinghua University have already talked about the water reuse. So we learned that reclaimed water is a water resource that can be reused for other purposes. So we can also see from here, from this figure, the different quantity and the purpose of reclaimed water reuse in China, especially in this part in the North China Plain, that it has been reused in large quantities for the landscape environmental reuse. So it means the reclaimed water has been discharged into the dry riverbed as ecological functions. But we also learned that this kind of discharge of reclaimed water to the dry riverbed and then further infiltrate into the groundwater is happening incidental aquifer recharge, which means the aquifer recharge is unmanaged. So for sure, it can increase the water quality, and also, as Professor Yanzhen introduced, is very cheap and energy efficient. So what about the water quality? Here we give an example of the Beijing River in the North China Plain. Here we can see from the dark line here in the North China Plain. Actually, 90% of the river flow here is from reclaimed water. So we can see here the water quality in the surface water is not good, it's below class 5. We can see from here. Besides this, we can also see there's pollution in the shallow aquifer, especially this part, just next to, very close to the river channel, where the pollution hotspot located. So we know the reclaimed water infiltrate from the surface water to the shallow aquifer pose high risks for the groundwater quality destroy. And so according to the Australian guideline for the water cycling in MAR project, these 4 different risks must be considered in the MAR project, especially the first one and the third one, which is related to the source water. And actually in our case is the reclaimed water. So the risks can come from the reclaimed water itself, and also from the reclaimed water reaction with aquifer minerals. So specifically speaking, there are 3 kinds of contaminants that we must be considered in this reclaimed water risks evaluation. So the first is the conventional contaminants like traditional organic carbon and inorganic nitrogen. And also the second is emerging contaminants, for example, trace organic chemicals like antibiotics, for example. And also the third one is the contaminants from reaction with aquifer minerals. So also, for example, the geological arsenic, iron, and manganese, etc. So these three kind of different contaminants will also be our focus in the next research. Actually, in our project, in our research, we still focus on the Beijing River, as I mentioned before, and is heavily affected by the reclaimed water. So first of all, we want to do a survey of the contaminants in the surface water and groundwater. So here we can see the river channel. So surface water was taken along the river channel. And also there are different sites, we call it groundwater monitoring site along the river channel, where there are different groundwater wells are installed, so from which you can take the groundwater samples. So overall, we can see there are different pollutants in the surface water and groundwater, like I introduced in the last page. So the conventional contaminants, like total nitrogen and total organic carbon, and emerging contaminants, like some trace organic chemicals. And also the geological pollutants like iron, we can see the increase in the groundwater. So besides the survey, we also do contaminant profiling measurement at the river cross section. So here at the Hehe site, which is also a riverbank filtration site. Besides the surface water sampling and the groundwater sampling I mentioned in the last page, we're also here at the part very close to the riverbank, which we call high break zone. So we also use piezometers for the pore water sampling. So we can evaluate how the water quality changes when there is a strong interaction with the surface water and the groundwater. And in the next page, I will show part of the results at the cross-section monitoring. We just take an example of the first figure. So we can see in the first figure, we can see the DO concentration, how it involved or how the DO was consumed from the river water here to the high break zone here, and then to the groundwater well, which is very far away from the river channel. So the DO was consumed. So also for the other contaminants like conventional contaminants and emerging contaminants and the geological pollutants. So here just briefly to explain a bit the results. So as a conventional contaminant, nitrate was consumed very fast from the river to the groundwater. And even though there's some increase in the ammonia here, it still can be consumed very fast in the groundwater. And also for the emerging contaminants, some are quite well removed, but some we can see should totally different changing patterns, like there is an increase here. And for the geological pollutants, we usually see a high increase from the river to the high break zone or to the even to the groundwater system. So in case of the water quality, we know that there's indeed some benefits of the water quality improve in this kind of unmanaged aquifer recharge, for example, the riverbank filtration system. But the risks from the emerging contaminants and from the geological contaminants, the risks are quite high, cannot be ignored. So will be also the focus of our next research, next study. So here in the next part of the study, we choose antibiotics, which is a very common trace organic pollutants as a representative for the emerging contaminants, because antibiotics are persistent and toxic, and they are high frequently detected in the Beijing River. And the studies show that even low concentration of the antibiotics can increase high antibiotic resistance. So that's why the removal mechanisms and the removal kinetics of these antibiotics should be studied. So that's what we did. We chose 3 sulfonamide antibiotics and collect different river sediments. And in the laboratory, we do the batch and column test. So the next, I will just briefly to show some results of our batch study. So 3 different batch studies I ever performed, including the sorption study, mineralization study, and the biodegradation study. And 2 different conditions were evaluated, like oxic and nitrate reducing condition, to mimic the field conditions in the reclaimed water environment. Then based on this, the contributions of different processes to the total sulfonamide removal can be evaluated. So here the figure just shows the results. the removal from sorption, from mineralization, from biodegradation, under different conditions and at different time during the experimental test. So we can see the green bar, which shows biodegradation was the main removal process. And the removal from sorption was on around 5%, and it is even lower in the mineralization process. And also we can see the green bar increase on the oxy conditions. So the biodegradation removal was increased with the time in oxy conditions, but decreased in the nitrate reducing conditions, which shows some complexity in the kinetic estimation. So we can also see here the SMX, one of the antibiotics we studied. The concentration was decreased. The concentration decreased with time in oxy condition, which is shown by the orange line. And in the blue line on the oxy condition, anoxic condition, it decreased first, but then it increased. So we think it's because of the retrosynthesis of the parent compound, which is SMX in our case. If there is no retrosynthesis, the concentration profiling probably will look like this. And based on the measurement, we can estimate the half-life. Here, the first order degradation kinetics was assumed. So we got the half-life on the oxy condition was around 15 days. And on the anoxic condition, the half-life was evaluated based on the measurements here. So it's around 50 days. So it's much longer than the oxic conditions. So we know that the sulfonamide and its derivatives can be quite persistent in the reclaimed water environments. Okay, so next, besides the laboratory study, we'll also do the field biodegradation test of this kind of antibiotics. So the study was performed at Tongzhou site in the North China Plain. Here is just an overview of the site, and these different points are the different like groundwater wells installed there. So we choose a well here 424 as an experimental well. So for the push-pull test with SMX, which also is antibiotics I mentioned in the left side. So simply to say is we prepare a stock solution of SMX and then inject to the aquifer, and then after storage some time and can pump it out to evaluate the recovery. And during the storage time, we took the samples, do the measurement, to see how the SMX concentration changed. So we can evaluate the nature removal attenuation of this compound. So based on the samples we took from the storage time and with the measurement of SMX and inert tracer bromide, we can calculate the half-life. And here we still use the first order. Not we, like the research group, also still use the first order kinetics. So from the experimental well, we estimate the half-life is around 4 days. And of course, we can also take samples from the observation well. So the half-life there was assumed to be around 8 days. So there are some difference here, but they still be comparable. But of course, it's different from the study from the laboratory because the different conditions in the lab and in the real field site. And lastly, I just want to briefly mention that we also do the risk assessment of some geological pollutants. So here I highlight inorganic arsenic because it is carcinogen. And there's indeed previous research has shown that there's arsenic pollutions in the artificial recharge system and also in this riverbank filtration system. So the concentration can be quite high than 1 ppb. So the influence of reclaimed water on the arsenic dissolution from the sediments must be evaluated, and that's also what we did. So we took the samples from the riverbed sediments, still the Beijing River actually, to evaluate the riverbank filtration system, and also the sediment samples from the aquifer at different depths to evaluate the artificial recharge system. And the sediments were taken back to the laboratory, incubated with the reclaimed water in the oxygen tests, and the samples were taken at different times to measure the arsenic release. And actually the results show that there are indeed some arsenic dissolution from the sediments. And also there is higher arsenic release from the riverbed sediments from the Beijing River and the aquifer sediments in the borehole. And we think we contributed a high resolution here to the high organic content in the sediments from the riverbed. And also another study is we incubated sediments with reclaimed water with higher DOC concentration, and we can see higher arsenic release happened. So our study indeed confirmed the arsenic risks, and also the risks from the geologic contamination happens in the reclaimed water infiltration environments. Okay, so just to wrap up briefly from the whole research, we know that the reclaimed water reuse in the North China Plain has led to some unmanaged aquifer recharge, which pose very high risks for the groundwater quality deterioration. And these risks not only come from the reclaimed water itself, but also from its reactions with the aquifer minerals. And on the hand, some conventional contaminants like the nitrate, as I mentioned also, can be quite well removed. But on the other hand, the risks from the geological contamination and from the emerging contamination, in our case, we highlighted the arsenic and trace organic chemicals as antibiotics. These risks cannot be ignored. So that's why the large-scale ecological reuse of reclaimed water must be managed with the North China Plain. Okay, so at the very end, I would also like to say, show our thanks to the projects, to the funding support from EU projects, from DANIDA, from P-Rural, and also from the China side projects from National Key Research Development Program, and also the National Geography Conservation Fund and the FC. And also, as Simon said, welcome to visit our page in the Mar China here. So that's all. Thanks. Thanks, everyone.
Thank you very much, Junji Ma, for your presentation. I think we will save any questions for later on, and we will go on to the next key speaker, Dr. Binghua Li from Beijing Water and Science Technology Institute.
I think I will start. Okay. I think I will, no.
Yes. It's okay?
Yes, we can see your presentation.
Good afternoon, everybody. I am glad to have a chance to the topic Development Technology Guideline for Ma, Beijing, Tianjin, Hebei region. It's about 3 parts. First part is regulation and guideline for Ma. In this table, there list a lot of regulation and Ma guideline. Some scale is regional. For example, Arizona, California, Florida. Some scale is national. For example, Australia, India, Italy, Mexico. And the most used Ma technology is aquifer storage and recovery, based in multiple and riverbank filtration. Among them, there are 2 guidelines was widely used in the world. One is American Society of Civil Engineering, the guideline for artificial recharge of groundwater. The other is Australia guideline for water recycling. For the American ACS, the object is to provide a standard system for the establishment, operation, and the maintenance of artificial recharge projects. And the scope is to standardize the planning, design, construction and maintenance, operation and shutdown of no national recharge system, so as to ensure the safety of groundwater. Meanwhile, the economic, environmental, and legal consideration, such as water rights, rules, regulation, as well as site investigation and testing procedure, are also taken into account. The recharge method can be through the surface infiltration or directly into the aquifer through the walls. As for the Australia guideline, it defined MA is the intentional recharge water to aquifer for subsequent recovery or environmental. The process management assured to protect the safety of human health and environment. Aquifer may be recharged by different techniques, including by wells, bands, cordially, or lever. And it point the risk management plan is the recorded document of MA. And it also points it is better to prevent the occurrence of risk than to clean up its influence afterwards. The aquifer recharge risk management is multiple barrier methods. Australia and WHO guideline for the Australia Aquifer Recharge Guideline assessments include the simple assessment procedure and the detailed assessment. The simple assessment procedure include the water and the suitable aquifer and space and the project, and the detailed assessment is includes 4 stages. Stage 1 is desktop study. It is to collect available information, data, undertake entry-level assessment, and so on. And stage 2 is investigation and assessment, include this. And stage 1 is construct and commission. And stage 4 is operation. Also, the Australia guideline provide steps for assessment, assessing aquifer recharge risk to human health and the environment. Both of them include 4 steps. Step 1 is identify the risk and the risk event. Step 2, assess the risk likelihood. Step 3 is assess the risk impact. Step 4 is discover the risk. Here is a relation between preventive measure and the critical control point is the left finger. And the relation between the target standards and the critical limit is the left finger. From the guideline, we get the recommendation parameter. It includes 32 parameter, actually Korea, and then nematodes, pH, temperature, conductivity, COD, and total dissolved oxygen, the TLC, total nitrogen, and the total phosphorus, and total suspended matter, total dissolved solid, and turbidity, ammonia, and the nitrate, and the sulfate, chloride, bicarbonate, sodium, potassium, and so on. And As for the Ma in China, China has carried out a variety of aquifer recharge practices, but the impact and risk of them on the ecological environment are not clear. And there is a lack of standards and safety control policies for Ma. There are only one relevant standard for aquifer recharge, and the quality of urban wastewater reuse for aquifer recharge, and one regulation for aquifer recharge in China, and the regulation on groundwater management. In the Article 43, government encouraged the use of scientific and reasonable methods to replenish groundwater in area that groundwater was our actual expectation. And for the law, there is a law of People's Republic of China on the prevention and the control of water pollution. It defines the aquifer recharge, various pollution source and human activity are restricted, including artificial aquifer recharge to replenish groundwater without deterioration of groundwater quality. The part 2 is why this region need Ma and the mass risk. In this region, water resources are shortage. The average amount of water storage resource is only 370 cubic meter, which is less than 1.3% of the country's total, but it carries about 10% of the country's population. Due to the water shortage and the long-term over-exploitation, ground reservoirs have accumulated a loss of 150 billion cubic meters, and the world's largest groundwater deposit funnel has been found. Thus, in this region, we needed the Ma. Under the support by Minister of Science and Technology, we get the recharge sustainable of groundwater resource fields in Beijing, Tianjin, and Hebei region. We found that the field with good recharge suitability are distributed in the alluvial and diluvial fan. In this figure, the green is suitability for recharge. Here. And this blue line is plain and mountain, divided plain and mountain. And we found that some risk for Ma in this region. As we all know, there are a lot of pollution source in the region. According to the 2015 environmental statistic Brut, the Haihe River Basin discharged a total of 8.47 billion tons of wastewater and 2.517 million tons of COD and 280,000 tons of ammonia nitrogen. The top 4 wastewater discharge in the industry were chemical, paper, food processing, the coal, mineral, and washing. The waste discharge amount for 49.1% of the total waste discharge. And the pollution component of groundwater are merely nitrogen, lead, chromium, and cadmium, mercury, and other heavy metal, as well as some organic for PAH and pesticide and other toxic and harmful organic compounds. Except besides this, the accumulated contaminants in the water zone and water log reaction will be affected during the aquifer recharge, which will affect the groundwater quality. Another risk is groundwater level risk rise caused by aquifer recharge may threaten the safety of existing underground water facility and structure, scale up subway and underground gas station, and underground storage tank, and sporadic landfill are scattered in the region. Excessive raising of groundwater will threaten the safety of existing underground water facility and as well easy cost solid waste to conduct groundwater. Municipal solid waste include construction waste, industrial waste, and domestic waste. The composition of construction waste is relatively simple, but the composition of industrial and domestic waste is complex and often contain a large number of toxic and harmful components, which will cause great pollution to soil and groundwater. Another risk is different water source and different type of aquifer recharge affect the ground quality in the recharge. We have found that the aquifer recharge, including artificial recharge, use external transfer water, rainwater flood, and water from reservoir. Natural recharge such as surface runoff and landflow, and unintentional recharge such as infiltration of water pipe and sewage. We compared recurrent water with groundwater and transfer water and found the analysis result of 258 trace organic showed that trace organic such as antibiotic in the recurrent water have far more species than those in the groundwater and transfer water, and the concentration were also higher. Meanwhile, we analyzed the rainwater and found that initial rainwater dissolved a large amount of acid gas. After landing on the ground, it contained a large number of organic matter, pathogen, heavy metals, the grease, suspended solid, and other pollutants.
Dr. Bingwa Lee, can I ask you to speed up your presentation and soon round off? Thank you.
Yes, we are. Okay.
Okay.
So we want to formulate some policies for the MAR to control the source water, the recharge, and the process of recharge. And here, this is risk identified and assessment identity index of MAR. And we clarified the right and responsibility of relevant department for MAR. And we formulate guidelines for the risk management and the control of natural infiltration biology for aquifer recharge in Beijing, Tianjin, Hebei. It includes 6 chapters and 34 articles. That's all. Thanks for your listening.
Thank you very much, and sorry for hurrying up on you. It's just so we can keep the time. We have now time for some questions, and I can see Mauricio asked a question to Simon, and I don't know whether Simon, maybe you can elaborate on the question.
Yes, I wrote a reply in the chat also for everybody else. Mauricio was asking a little bit about the depth of the wells and the aquifers. And typically our models go down to 200 to 300 meters. And we have most information about the shallow aquifer, both from boreholes and also from the groundwater level observations. So we have more details in the upper 50 to 100 meters of the aquifer. I hope that answers the question.
Yes, thank you. And then we have another question from, I can't see who it's from, but it's to Professor Lee. And a question about the specific criteria for grading suitability of recharge in Beijing, Tianjin, Hebei region.
We get a formulate. It includes the economic profit and the environment profit and the natural profit. And we use the HP to select the parameter and give this to a professional person to get the, how to say, 权重.
Weighting, or we have experts to help us to develop the weightings for the
Yes.
criteria.
Thank you for the interpreters. And anyone else who wants to have a question or raise hand for we have time for questions. Yes, there's one.
Yeah.
Yeah.
So and Binghua, I have a question for you. So can you maybe just describe a little bit of the difficulty of trying to get the guideline through? Because I mean, it's definitely very much needed. What's the next step? You know, because MARI is complex, it involves all these different government agencies. What's next?
Can he speak in Chinese?
Yes, if Binghua wants to speak Chinese, it's okay. Then maybe we can have the interpreters to, if that's what. Yeah.
Yes, of course. Well, right now, a challenge we have to grapple with is on how can we define which department is responsible for what, particularly for a program to run at the planning stage, at the construction stage, and for the water resources that is going to be transferred, and at the operation stage, at each and every one of the stage, which department is responsible for what. It's hard to decide how the powers are delegated or distributed across departments. Right now in China, the approach is we proceed with the program first. For many of the program we have, MAR program we have, they are referred to as pilot or experimental MAR, but for us, it's still a major project. But if we are truly considering them as an engineering project, then environmental assessment, impact assessment, and all of these studies need to be in place. But then you have to deal with multiple departments, including NDRC, including the health authority, environmental authority. So if MAR programs are defined as an engineering project now, and then we really come to standardized authority, standardized practice, then the biggest challenge comes to who is in charge of what.
Thank you. I think we have another question here from Anna Maria. She has a question for Yunji Ma about the source of antibiotics.
Maybe 在这边来说吧。Okay, this one's better.
Sorry.
Where is the question? Here. Analyze the source of the antibiotics. Actually, now we think the antibiotic is the groundwater. For sure, it comes from the reclaimed water, because reclaimed water always have this kind of trace organic pollutants, and it's very difficult to remove this in the traditional wastewater treatment plants. So the effluents will contain a lot, then go to the aqua environments. And can the content of antibiotics be reduced at the source or in the treatment of reclaimed water? Yeah, that's one question when related to the antibiotic can be reduced at the source is the antibiotic from the reclaimed water, but it is very difficult to remove from the wastewater treatment plants, like by the traditional wastewater treatment plants. So it's very difficult actually. Can it be removed in the reclaimed water? Actually, studies show that the different antibiotics, they have different removal performance in the reclaimed water, just in the nature system. So for example, if you know the antibiotics of ibuprofen, I think it's can be very good removed. But for the sulfonamide antibiotics I was studied also is quite challenging, even in the treatment of the reclaimed water. So I hope this answer can help you a bit with this. Thanks.
Thank you. Maybe we just allow two more questions, but then we have to move on because we have to, the next speaker has to leave before 6. So Enrique has asked a question about detected any effect of MAR on end users, control of the demand. I mean, is MAR pushing any control of the demand in your area of study? And this is to Binghua Li.
我知道这个问题很好。
Yes, I see. This is a very nice question. In our assessment, when we evaluate the south to north project, we already evaluate the Pinghua River Basin effect for MAR, because this is a basin that provides a source of water for the entire region for multiple purposes. And with MAR, we have already greatly improved on the water table, groundwater water table already. And also because the water quality of the south to north transfer project is quite good. So once they are used for replenish of the groundwater, and once it mixes with the existing water body, it helped to further improve the water quality in general in the basin. And also because of overdraft, we have seen land and soil subsidence in parts of the region. But starting from 2018, and between 2018 and 2020, we have replenished 200 million cubic meters, and that has slowed down the land subsidence in this region. And also, we have noticed that in certain sites in this region, we have even seen the lifting of the many parts of the region. that help to revert land subsidence quite greatly. So these are some